Hello, this is Mrs. Ward. I'm going to go over the homework from section 1.4, which is continuity and one-sided limits. So numbers 1 and 6, they want me to look at the graph and determine the limit and discuss the continuity of the function. So there's three parts: the limit as x approaches c from the right, the left, and then the limit overall. So number 1, c is equal to 3. So part A wants me to find the limit of f of x as x approaches 3 from the right. So graphically, as I'm coming from the right, that limit appears to be 1. Part B wants me to find the limit of f of x as x approaches 3 from the left, and that is going to also be 1. Since these two are the same, then this is C, the limit of f of x as x approaches 3 and with no direction is also going to be 1. You will notice if I erase this, you will notice that it is continuous. I mean, f of 3 is 1. There's no jump. It's a continuous function. So that's the next thing I'm going to say that it is continuous. Okay, number 6, if I go to do this one, part A, I'm going to find the limit of f of x. This time c is equal to -1 as x approaches -1 from the right. So coming from the right, that appears to be 0. Part B, find the limits of f of x as x approaches -1 from the left. Coming from the left, that appears to be 2. Part C, find the limit of f of x as x approaches -1 without a side, so just the limit overall. Since it approaches two different numbers from two different sides, I'm going to say that this limit does not exist. Since the limit does not exist, I know the function is discontinuous, so it is going to be discontinuous at x is equal to -1. And then because the limit doesn't exist and I have that jump, I'm going to say that it's a non-removable discontinuity. Now, I'm sure I spelled that wrong. Okay, number 9, it says find the limit if it exists. If it does not exist, explain why. So as I'm taking the limit of x as x approaches -3 of x over x squared minus 9. I graphed it. I figured that was the easiest way to do it. It is discontinuous at -1, but it ends up being an asymptote. So when I approach -3 from the left, it decreases without bound. In other words, it is an asymptote that as I approach -3, it just goes down. So I'm going to say that this limit does not exist. I graphed that to get that. Number 2, I graph it again. So when I do this, I ended up with, as I'm approaching 2 from the right, so this will be a positive over positive. This will end up being 1. And so that limit will be 1 from the right. If I were approaching 2 from the left, it would be -1. The overall limit doesn't exist, but because of this direction, approaching from the right, that one-sided limit does exist. Number 18, find the limit as x approaches 1 from the right, so numbers that are greater than 1. So since I want numbers that are greater than 1, I am going to use the part of the formula that has x is greater than 1. So I am going to do 1 minus 1, which would just be 0. So that limit is going to equal. So the limit of f of x as x approaches 1 from the right will be 0. The next one, the limit of 3 times the greatest integer x at -5 as I'm approaching 4 from the left. So if I'm approaching 4 from the left, I'm going to want a number that is smaller. So this will end up being 3. And then if I do the greatest integer of like 3.99, because that would be to the left, minus 5. So this would be 3 times 3 minus 5. So that would be 4. So this limit would be 4. Again, I could do that graphically as well. Numbers 25 through 28 discuss the continuity of each function. I'm looking at the graph. So if I'm talking about whether this function is continuous or discontinuous, I'm going to say that this graph is discontinuous. And there's two places where it's discontinuous. One is going to be x is equal to -2. The other place is x is equal to 2. And then if it wants me to talk about more about the discontinuities, since they are both asymptotes, so I'm going to say it's discontinuous because f of -2 and f of +2 are undefined. And since they're both forming asymptotes, I'm going to say that they are non-removable discontinuities. Number 26, I'm looking at the graph, discussing this. I'm going to say that it is discontinuous at x is equal to -1. I am going to say the reason for that is because f of -1 is undefined, because I have that hole there, and I'm going to say that that is a removable discontinuity. '28, I'm going to say the function is discontinuous at x is equal to 1. That's really bad at. The reason is because the limit of f of x approaches 1 does not equal f of 1. That makes sense to me. I hope that makes sense to you. And it is a removable discontinuity. Okay, the next one, 28 and 29, discuss the 29 through 32, discuss the continuity of the function on the interval. So if I'm looking between -5 and 5, it is continuous because -5 will work and +5 will work. Everything in between will work. I probably would graph this, and if I graph this at -5 and +5, I'm going to have like this half circle thing. So it is going to be continuous. And the reason why it's also continuous is because I can take the square root at 5 and at +5, so this closed interval is okay because I can use both -5 and 5. The next one says discuss the continuity at -1, 2. So if I were to do this, I would say x squared minus 4 cannot equal 0 if we're going back to the way we used to do things. So I'm going to say x squared cannot equal 4, so x cannot equal ±2. Since -2 is not a problem because -2 is not in this interval, but this 2 is in this interval. So it's not continuous over this interval. It would be continuous over the interval where I do not include the 2. So I can write something like that where it's not continuous here, but is continuous here. And the reason why it's continuous here is because I'm not including that 2. I'm going up to that 2, but not including that 2. Find the x value of any at which f is not continuous. So if I'm taking the cosine of pi over 2 times x, cosine is continuous everywhere. And pi over 2 times that is, pi over 2 is continuous. So this function is going to be continuous. And so that's a continuous function for all x. The next one, x minus 3 over x, the absolute value of x minus 3 over x minus 3. The only place that it's not continuous, it is not continuous at x is equal to 3, because that makes that denominator equal to 0. Is it removable? Yes. No. No, it's not removable. I wrote removable. It is non-removable. Because if I remember correctly, as I'm approaching 3 from the left, it's going to be -1. As I approach from the right, it's going to be +1. So that is a non-removable discontinuity. And the reason why it's a non-removable discontinuity is because the limit of f of x as x approaches 3 does not exist, because from the left it's equal to -1, from the right it's equal to +1. The next one, tangent. So tangent is not, so the pi over 2 just throwing you off, because pi over 2 is continuous everywhere, but the tangent of a function is not continuous everywhere, because tangent, remember, is sine over cosine. So your tangent is not going to be continuous when your cosine is equal to 0. So this is going to be the cosine of pi over 2. This is going to be the sine of pi over 2. And so that's going to be, so cosine of pi over 2 times x. Well, the cosine is actually equal to 0, is equal to 0 at normally pi over 2 and 3 pi over 2. So I'm taking x and times that pi over 2. So this has to be an odd number, because if it was an even number, then I would be 1 or -1. So I am going to say that this is discontinuous at, and then I want odd numbers. So to do odd numbers, I'm going to say at 2k plus 1, where k is a integer. So that'll make sure that that's an odd number. And because if you remember your graphs, that forms an asymptote, I'm going to say that it is a non-removable discontinuities, because I have those asymptotes that are formed there. So you got to remember which trig functions have those asymptotes. So sine and cosine do not have asymptotes. Everything else does. Number 62, I want to discuss the continuity of the composite function. So I want to do h of x, which is f of g of x. So this is f of g of x. I have to write that for some reason. So this is going to be f of x minus 1. So this is going to be 1 over the square root of x minus 1. That's going to be my function. And it will be, this has to be, so x minus 1 has to be greater than 0, because I can't divide by 0, which means x has to be greater than 1. So it is going to be continuous. Why can I not spell this word, I wonder? Continuous at, I can start at 1, x is greater than 1 to infinity. And then it's going to be a parenthesis here, because it has to be greater than, not greater than, or equal to. So those are all the places where that function, where that composite function is continuous. The next one, describe the intervals on which the function is continuous. This one, since this x squared plus 1 has to be greater than 0, which means x squared has to be greater than -1. Well, that's going to happen all the time. So this is going to be a continuous function always. So I can either write I can say always, or I can say, whoopsie, or I can say from -infinity to infinity. And I like the interval notation, so I'm going to write that. Secant is 1 over cosine. So this is pi over 4 times that. So Oh, and I see that it's 2 and -2, that it's discontinuous, and that they took care of that for me. So now I'm going to say that it's, so it would be continuous from -2 to 2, because that's the interval where I have this. But then the next time I'm going to have an asymptote, as you should know that these little parabolas are about the same, and there's 4 units here. So the next one will be at 6 here, and I will have this other asymptote. So I'm going to say that it's continuous from 2 to 6, and then probably 6 to 10, dot, dot, dot. And going the other way, the other one would be from -2 to -4, dot, dot, dot. And that's the places where it is continuous. Well, this should be -6. My bad. 4, -6. I was thinking 4 rows. You know what I'm doing. All right, the last one. Explain why the function has a 0 at the given interval. Well, the first thing I'm going to do is I have to say that this is a continuous function on the interval 0, 1. And the reason why it's continuous is because it makes a shape that goes like this, if I remember correctly. And there's no places where it would have a 0 for the denominator, no asymptotes, anything like that. So I know it's continuous on that interval. If I find f as 0, so I'm going to put 0 into this, and I get -2. If I put f of 1 in here, I'm going to have 1 plus 3, that's 4 minus 2, and that is going to be a +2. So what this is saying is if I graph 0, -2, and then the graph does something, I don't know, and at 1, I go to 2. Since it's continuous, then somewhere between this point here and this point here, I'm going to have to cross the 0. I have to. That's what the intermittent value theorem says. So what you have to do to show this is you have to say that it's continuous on the interval that they give you. Then you have to show that if they want a 0, you have to show that 1 is negative, 1 is positive, and then you've shown that it has to cross 0 because 0 is between a negative number and a positive number. Okay, I hope this helps, and I will see you next time in class.